All right, so we are going to work on the Unit 3A review chart. So this part of Unit 3, which was our huge unit that lasted forever, was factoring. So I'm going to start by going through factoring. So we're going to do most of this first page, I think, in our first video. So first up, we started learning factoring by GCF because that can be in any type of problem. So it doesn't matter how many terms, it doesn't matter if there's a leading coefficient or not. Factoring by GCF is basically just backwards distributive property. So what we're going to do is we're going to look through this example right here, and we're looking for what number can be divided into all of these. So between the 6, the -3, and the 12, they can all be divided by 3. And now if we take a look at the variables, the way the variables work when we factor with GCF is we are looking for the smallest exponent, and that will be the most that's in common. So right here we have a squared, this one's a cubed, this one's just a. So they all have at least one a. So now we go through and check for the b's. So this is b to the 5th, this one's b to the 3rd, this one's b squared. The smallest is b squared, so that is the most that they have in common. So now what's going to happen is in parentheses, we're going to put what is left over, meaning that if I distributed this back out by multiplication, I need to end up with this trinomial. So in order to get 6a squared b to the 5th, I would need to multiply this by 2a b to the 3rd. All right? In order to get -3a cubed b cubed, I would need to multiply this by a -1 a squared b. And then in order to get 12ab squared, I would need to multiply this by a +4. So once I distribute that back out, I would get what I started with. All right, so factoring GCF always comes first. It's what we always do first because it is one that can be in any situation. All right, I'm going to try and get this in better focus. It doesn't look that good to me. Okay, all right, that looks better. All right, next up, we're going to go to looking at factoring trinomials. So what we did here is we were looking for numbers that multiply to be 15 but add up to -8. So if you think of numbers that would multiply to be 15, I can think of 3 and 5 or 1 and 15, but what would add up to -8 would be these two if they were both negative. So I know that this factors to be m-3 and m-5. And the way you can check any factoring problem is just to multiply back together. So just distribute back. So if I multiplied m times m, I'd get m squared. M times -5 would give us -5m. -3 times m would be -3m, and that's where the -8m comes from. And then -3 times -5 would give us the 15. So that's just a way you can check. All right, so on this one, again, looking for numbers that multiply to be -28 but add up to +3. So when I'm thinking of numbers that multiply to be 28, 4 and 7 come to mind immediately. In order to get a -28, when I multiply, one of them has to be negative. But in order to get a +3, when I add them together, it would have to be on the 4. So I know that this factors to be n-4 and n+7. And again, if you just distribute that back out, multiply it back together, you can check your answer. All right, next up is factoring by grouping. So you can always identify grouping because there will always be 4 terms. So grouping always has 4 terms, easy to identify. And what we can do is group them as 2 groups of 2. Now, you might not always be able to group them the way they're written. So you just have to pay attention. You need to make sure that they have something in common. Once you have your two groups of two, we're basically just going to do GCF 3 times. So I'm going to cover this up. GCF between these two would be a 5n squared. And if we take that out, we would have 5n minus 1 left over. All right, so now I'm going to look at this group right here. So the GCF between these two is a 7. And if we factor that out, we get 5n minus 1. So that's not a coincidence. Now I have a common factor of 5n minus 1. So we know that's one of our parentheses. And then the other one we'll get from the GCF of each group. And again, if we distribute this back together, we'll get what we started with. All right, so next up, so on this one, I'm going to group those two and those two. All right, so out of the first group, there is a GCF of 20x, and that is going to leave 4y minus z. All right, if I look at these two, there's a GCF of 4w out of both of these. So if I take out a 4w, all right, if I take out a 4w, that's going to leave a negative 4y, which isn't going to match. So that means I need to take out a negative 4w, and then what would be left over would be 4y minus z. And now I have a common factor right there, so I know 4y minus z is one answer, and then 20x minus 4w would be the other. All right, next up, we're going to look at factoring with a leading coefficient. So we did these a little bit differently. I just call it the big X. I know some people call it like X Games, but I like to do this one when there's a leading coefficient, because we did trinomials up here, but we didn't have to worry about getting another number because the coefficient is 1. But right up here, we have to pay attention because we need to get 4x squared, not just x squared. So I'm going to make the big X. So I'm looking for numbers that multiply to be 36, but add up to 12. So numbers that multiply to be 36, but add up to 12. So that would be 6 and 6. All right, now, since we have a leading coefficient, I need to factor that back out, so I need to reduce this back down. So both sides end up being the same, and I get 3 over 2. So hopefully you remember that that now becomes 2x plus 3, and I have that one twice because I ended up with the same answer. So another way we could write this is 2x plus 3 squared. All right, so let's try this one. So first, make the big X. So I'm looking for numbers that multiply to be negative 30 that add up to negative 7. So I need to multiply and get negative 30, but add up to negative 7. And I can do that with a negative 10 and positive 3. So if I multiplied those two, I would get negative 30. And if I added those two, I would get negative 7. But since I have a leading coefficient, I need to divide that back out. So this one will reduce to negative 5, so that's one answer. That one won't reduce. So now to change this back into two binomials, this one is just going to be c minus 5. This one will be 2c plus 3. And again, you can check your answer by multiplying this back together. All right. Difference of squares. So difference of squares is a special one because what happens in here is we don't have a middle term. And the reason why we don't have a middle term is because it cancels out to 0. So if you want to think of it as like we did right up here with the big X, we're looking for numbers that multiply to be negative 121 but add up to 0. So what happens here is they end up being perfect squares, and that would be because negative 11 and positive 11, if I multiplied those, I'd get negative 121. If I add them, I get 0. So this ends up being n minus 11 and n plus 11. So what happens in difference of squares is it's almost identical, except one of them's positive and one of them's negative. All right, so right here, same idea. So I don't need to multiply all this out and do the big X. I know that 9c squared is a perfect square, and 49d squared is a perfect square. And since they're negative, one of them has to be positive and one of them has to be negative. So in order to get 9c squared, I need a 3c and a 3c. In order to get a negative 49d squared, I need a negative 7d and a positive 7d. And there you have it. And again, if you multiply those back together, the middle cancels out because one of them will be negative 21 and the other one will be positive 21. All right. Now we're going to look at factoring completely. So this is kind of a combination of everything that we've done on this page right here. So when we factor completely, the first thing that we need to do is look for a GCF. So I'm going to look for a GCF, and I can see that both of those can be divided by 3. If I take that out, that would leave x squared minus 4. So now what I need to do is see if that can be factored anymore. And what I notice here is that this is a difference of squares. So I can break up x squared to be x, and I can break up negative 4 with a negative 2 and a positive 2. So what happens is when I multiply this back together, the middle number will cancel out and disappear. All right, next up. So first thing I'm going to do is look for a GCF, and I can see that all of those can be divided by 5. So I'm going to take that out. That'll make the problem a little bit easier. So now I'll have 10a squared plus 7ab minus, minus 6b squared. Almost wrote 30. All right, so I just factored out a 5. Excuse me. So now I have 10a squared plus 7ab minus 6b squared. So now what I have is a trinomial with a leading coefficient. So I'm going to jump over here and make a big X. So I'm looking for numbers that multiply to be negative 60, but add up to positive 7. So if you think, all right, one way to get 60 is with 6 and 10, but that's not going to help me get the 7. So we need to think of another way. And we can get negative 60 if we multiply 12 and 5. One of them has to be negative. But in order to get a 7, I need the 5 to be negative. So now I can multiply to get negative 60 and add them together to get 7. But remember, we had a leading coefficient, so we need to divide by 10. All right, this one, I didn't leave enough space. This one reduces to be 6 over 5, so there's one answer. This one would reduce to be negative 1/2, so that's our other answer. So to write this in two binomials, the denominator comes out front. So that's going to be 5a plus 6b, because I have to get the b squared. And then this one would be 2a minus 1b. And then if we multiply this back together and then take that answer and multiply by 5, we'll get what we started with. So this is the final answer. So just keep in mind that you took that 5 out from the very beginning. So if we multiply this together, it's not going to get us back to the original problem unless we also distribute a 5. All right, so last thing, we'll go ahead and finish this, I guess. Excuse me, solving by factoring. So what happens on solving by factoring is basically we are going to go one step further and figure out what the value of x is. We do that by factoring. So first thing we're going to do is we have to get the problem equal to 0. So I'm going to move this onto the other side by subtracting 8 from both sides. Now what I want to do is factor this down. Well, this is a trinomial. There's no GCF. So I'm looking for numbers that multiply to be -8, but add up to -7. So if I multiply -8 by a +1, I'll get a -7. So this is the factored form, but now I'm solving. So what happens is I'm going to set this one equal to 0, which means x equals 8. Or I'm going to put this one equal to 0, which means x is -1. So those are my two solutions when I solve. And if you remember, I showed you that the exponent will tell you how many answers you should get. All right, moving on to the next one. So I have a trinomial, but I also see a GCF of x. And I can see right here that I need 3 answers. So the first thing I'm going to do is take out an x as a GCF. So that would leave x squared plus 4x minus 12 equals 0. So now I need to factor this. So this is a trinomial. I already took out the GCF, and there's not a leading coefficient. So I'm looking for numbers that will multiply to be -12, but add up to 4. So if I use a +6 and a -2, I'll get a -12 when I multiply and a +4 when I add. So now I need to set each of them equal to 0. So that one equals to 0, so that's already the answer. If I put this one equal to 0, then x will be -6. And if I set that one equal to 0, then x will be 2. And those are my 3 solutions. So when we solve by factoring, we go through, we factor the polynomial, and then we set each of them separately equal to 0, and that will give us an answer for each part that has a variable like an x that we're solving for. All right, so that takes care of factoring, which is a huge topic that you are going to be using for the rest of your math career for sure.